Alrighty, so we're going to focus on applications of the ideal gas law here. In this first problem, they collected a bunch of data about some gas, but they're uncertain as to whether it's nitrogen oxide or dinitrogen oxide. So we're going to use that data along with the ideal gas law to figure out which oxide it is. So the way I like to do these, I like to go through the problem and label all the given information. So I have a 1.27 gram sample, so that's mass. And it occupies a volume. And then we're given temperature. And the 737 millimeters of mercury will be my pressure. So I have PV, I have T. That gives me enough information to solve for N, for the moles. I'm going to hold off on using the mass. So I think if I could figure out the molar mass, which we know has units of grams per mole, then we would be able to identify the oxide. So if I put these grams on top, and then use the ideal gas law to solve for moles, and I'll put that in the denominator. So let's get to work. First thing, I'm going to isolate N by dividing both sides by RT. So I wind up with N equals PV over RT. Plug in all my given information. So pressure, I wound up converting to atmospheres, because remember, when you use the ideal gas law, you always have to have the units of whatever you're plugging in match the units of R. So we're going to use 0.969737 atmospheres times the volume, which is 1.07 liters, big set of parentheses up here, divided by 0.08206, my R value, liters times atmospheres over moles times Kelvin, times the temperature, which I made sure to convert to Kelvin. So we're going to use 298.15 Kelvin. With these, as with all equations, right, we always want to check our units. So atmospheres will cancel with atmospheres, Kelvin with Kelvin, liters with liters, and then we have moles on the bottom of a double fraction. So that gets flipped up to the top. When I did this earlier, I got a value of 4.241 times 10 to the negative 2 moles. Kind of cutting it off a little bit there, but I would definitely pull up the longer value in my calculator for this next step. So we're going to calculate the molar mass by taking the given grams and dividing by our mole value. So I'll do 1.27 grams divided by 4.241 times 10 to the negative 2 moles. And at the end of the day, I got a molar mass of 29.9 grams per mole. So we need to determine which oxide was produced by the reaction. And if we get the molar mass of nitrous oxide, it's pretty much 30 grams per mole. This one is much higher because it has 2 nitrogens and 1 oxygen. So because this molar mass is 30 grams per mole, I'm going to say that nitrous oxide was produced by this reaction. So I really firmly believe that you shouldn't memorize formulas to solve these problems. So granted, in most textbooks, online, you'll see formulas for density, for molar mass of a gas. However, my issue with it is, will we remember how to use these formulas long term. So in 2 to 3 years from now, when you're taking an entrance exam for medical school or for graduate school, will you remember the formula for density? Probably not. But if you develop a way of approaching the problem just using PV equals nRT, then you'll be able to solve it for the rest of your life. So that's why I present it this way. So in this problem, we're asked to solve for the density of helium gas. And so I'm thinking density, and then, this is one formula everyone will remember forever. Density equals mass over volume. So we need a mass and we need a volume. They gave us a temperature and they gave us a pressure. The other thing they told us is that it's helium gas. So because I know the identity of the gas, I know its molar mass, which I just grab off of the periodic table, right? Helium gas is a monoatomic gas. So just one helium, 4.0026 grams per mole. All right, so lots of information, even though it seems like it's not that much at first. All right, since it's a gas problem, I always lean towards ideal gas law, almost every single gas problem. However, as we're looking through this, let's see, we got temperature, I'm going to check it off. We have pressure, check. R, of course we have R. And so we don't have volume and we don't have moles. So what I'm thinking and what my approach is going to be is maybe I can create some kind of conversion factor by putting volume and moles on one side and then putting everything else I know on the other side and plugging values in. So I'm going to divide over the n, and I get P V over n equals RT. And then because I know P, I'm going to bring it over with the rest of the stuff that I know. Divide both sides by P. So I have V over n, which I don't know anything about, but it'll be a conversion factor for me, equals RT over P. So I'll just start plugging stuff in because it looks like we have the right units. We'll do 0.08206 liters times atmospheres over moles times Kelvin. Our temperature is already in Kelvins, perfect. So 298 Kelvin. And that's going to be divided by the pressure, which is already in atmospheres. So 0.987 atmospheres. Alrighty, so plugging this all into my calculator in one step, I'm going to need parentheses around the top there. My approach to pretty much every single science problem works because I always follow my units. So let's continue to do that. Atmospheres will cancel atmospheres, and Kelvin will cancel Kelvin, and then we're left with units of liters over moles. And that makes sense because we, redistributed everything, solved for volume over moles, so liters over moles makes perfect sense. Plug all that into your calculator, and you're going to get a value of 24.77596 liters per mole. So at the end of the day, I want to solve for density. Density is mass over volume. So maybe grams over, typically we do grams over mils, right? But I'm not really seeing mils or milliliters in here. So can I get grams over liters? That'll be my destination unit. And we have liters over moles, and then over here we have grams over moles. So maybe we can use those two and cancel out the moles, right? Since I want grams in the numerator, this is my goal. I'm going to start with my molar mass, 4.0026 grams per 1 mole. And then I need to get rid of moles. So I'll have moles up top so it cancels. And I need liters in the bottom. So I'm going to take this value and put it in the bottom, 24.77596 liters per 1 mole. So divide the grams by the liters, the 24.77596 liters, and we get a density of 0.162 grams per liter. Alrighty, so this problem must have been a test question at some point. It is such a cool problem. It's got this throwback aspect to it where in order to find the formula and name of the gas, we have to consider the products of the double displacement reaction between hydrochloric acid and sodium sulfide. So we're going to break the hydrochloric acid into its ions, so H plus and Cl minus. The sodium sulfide will be Na plus and S2 minus. And then we're going to do-si-do them. So we'll have the hydrogen recombine with the sulfide and the sodium combine with the chloride. Make sure you get the positive ion first. So sodium chloride will definitely be one of the products. In addition, make sure you're considering the charges. So here we have a +1 and a -2. So the 2 is going to crisscross down and we'll get H2S. And that's going to be our gas. We know sodium chloride is a soluble salt. We know it's not foul smelling. So we know that that's the gaseous product they're talking about. What's the name of it? It's a binary acid, right? So anything that has anion with H is considered an acid. Anything that produces H plus. And it's binary because instead of combining with a polyatomic ion, it's just combining with something off of the periodic table. So binary acid. And remember, for binary acids, we're always going to do hydro and then the name of the element. So this is going to be hydrosulfuric. We do the ic ending on the binaries. Acid. Alright, so even though we found the formula and figured out the name of the gas that's produced, I still want to verify the molar mass. I mean, obviously we could figure out the molar mass off of the formula, but let's verify it using the given information. So just like on the other problems, I'm going to go through, I'm going to read and figure out what they gave me. So we have a volume and we have a mass, and we're asked to calculate the molar mass. So right off the bat, I'm thinking my final answer needs units of grams per mole. They also told us that the reaction was done at STP. And so the temperature then would be 273.15 Kelvin, and standard pressure is just standard atmospheric pressure. You know, any reaction that you do in an open beaker is going to be done at 1 atmosphere of pressure, so we'll plug in that as well. So I'm going to use the ideal gas law, PV equals nRT, but I want to solve for moles, which I'll put in the bottom. So plugging everything in, we're going to have a pressure of 1 atmosphere, a volume of 1 liter, R is 0.08206 liters times atmospheres over moles times Kelvin, and then the temperature 273.15 Kelvin. Just checking how everything's canceling, making sure I set it up right. Liters with liters, atmospheres with atmospheres, Kelvin is gone. Leaves me with moles on the bottom of double fraction, and that'll get flipped up to the top. So for this problem, I got 4.46136 times 10 to the negative 2 moles. I'm going to take that in conjunction with the grams. I'll put the grams in the numerator and that value in the denominator to solve for my molar mass. So 1.52 grams divided by the 4.46136 times 10 to the negative 2 moles. And I wound up getting a really nice number, 34.1 grams per mole. Beautiful, right? Because sulfur comes in at 32, and then you got the 2 hydrogens, so you could definitely justify that molar mass.